AC power and the calculation of power in circuits that are represented either with AC signals in the time domain or with AC signals in the phasor domain. So basically, to put this in perspective, the AC power unit is, once you understand the basics, it's a little bit of a collection of formulas. So I'm going to point out as we go through this lecture how many of the formulas that we see actually represent the same thing. It's just that some of them are more useful to use at some times other than others. I also want to comment that this is taken from a different textbook. You primarily have the textbook material contained within these PowerPoint lectures. This is taken from the Nielsen book. I believe they do a significantly better treatment of AC power than the Alexander textbook. So the first thing we want to start with is a review of what a phasor diagram is. We just have several phasors listed here, shown basically here in sort of the statement, that paragraph before the figure. We're just going to illustrate as a phasor diagram each of these phasors. So the phasors, as you recall, represent a magnitude and a phase angle. In a phasor diagram, as in the kinds of complex plane representations that you will use from here on in electrical engineering, we use the complex plane where the vertical axis is the imaginary axis and the horizontal axis is the real axis. So if this were given in rectangular form, the real part of the complex number would be marked off on the real axis, the imaginary part on the imaginary axis, and it would be like a line to a point with two components. The only difference here is that instead of rectangular components x and y, we have phasor components, real and imaginary. So in phase and magnitude form, if we have 10 angle 30, we always measure that phase angle counterclockwise from the real axis. So 10 angle 30 is illustrated here. You notice the length is 10, the phase angle that it makes is 30. 12 angle 150, we draw our phase angle once again clockwise from the real axis, end up at 150 degrees with a magnitude of 12. Note that this one looks longer. Now I want to comment about these last two because it's standard in electrical engineering and phasor notation to only run your angle between plus and minus 180. So for example, instead of 190 degrees here, we actually switch that and give the negative equivalent because remember we're 360 all the way around, so 190 is actually the same angle as negative 170. So if the phase angle is negative between 0 and negative 180, then obviously we go in the negative direction for the phase, and so the minus 170 is then measured clockwise from the real axis. So here's where 8 angle 170 would plot out. And then finally, 5 angle minus 45 is plotted here. Now, I want to talk a little bit about leading and lagging. So, one phasor leads another if it is a farther rotation in the counterclockwise direction and its angle is less than 180 degrees, the angle between the two phasors. So for example, 12 angle 150 here leads 10 angle 30 because it is farther along in the rotation and the angle between the two phasors is less than 180 degrees. This 8 angle minus 170, also notice it is farther along in the rotation and the angle between it and the 10 angle 30 is less than 180 degrees. So we would say the 8 angle minus 170 leads the 10 angle 30. Now let's look at these last two. Okay, in this case, yes, it is farther along in the rotation, but if I look at the angle in this way, it's greater than 180 degrees, which is not one that we consider. So I need to look at this angle. Okay, in this case, if I look at the angle that is less than 180 between these two phasors, then the 10 angle 30 is leading the 5 angle minus 45. So if we look at some other examples, based on looking at just two of these at a time and looking at which angle is less than 180, the 5 angle minus 45 would lead the 8 angle 170. The 5 angle minus 45 would lead the 12 angle 150, because notice this is the smaller, this is the less than 180 angle. But the 10 angle 30 leads the 5 angle minus 45. So hopefully that just gives you a visual of leading and lagging. We're going to use those terms when we talk about AC power. So I wanted to do this brief review of the phasor diagram, which is also sometimes useful to use. And this concept of leading and lagging, it's referring to the relative phase angles between two phasors. All right. So we're just going to use the following representation of a circuit for calculating power, very similar to the one we used at the beginning of the semester when we were calculating power for a DC circuit. An AC voltage and current can be written as follows, where we have V is some magnitude cosine omega t plus a phase, and I is represented in the same way. So if we're going to use the passive sign convention referring to the figure, the instantaneous power is V times I. So the word instantaneous is used to represent as a function of time. So an instantaneous voltage, for example, would be the cosine form in the time domain. An instantaneous power would contain time as a variable and allow you to calculate that power at any instant of time. So the first thing that we want to do is we want to make this a little easier on ourselves, and we want to set one of the phase angles arbitrarily equal to 0, because since this is a steady state sinusoidal function existing from minus infinity to infinity, we have the ability in making our definitions to choose the reference for 0 time. So what we're going to say is that the current peaks at t equals 0, and we're going to take what was the current phase angle and we're going to move it to the voltage signal. So all we really did here is we really just shifted the t equals 0 axis, the time axis, to where the current has 0 phase angle. And now the phase angle on the voltage is the difference between the original phase angle on the voltage and the phase angle on the current, because we basically shifted both of them by minus theta I. This is just going to make the trig a little bit easier. So now to find the instantaneous power, we take V, we multiply it by I, and we get the following expression. Now this expression is not particularly useful because we've got this mixture of phase and time. So we're going to apply a couple of trig identities. What we're going to end up with is an expression that looks more complicated, but it's actually, even though it's longer, it's actually going to be much simpler, because individual terms of this expression are going to represent things that are physical. Right here, we don't really have anything that we can pull out as far as being a physical representation of something. So let's look at what we're going to do trig identity-wise. So the first thing we're going to do is we're going to work on this angle, and we're going to use, because we have a product of two cosine functions, we're going to use the trig identity cosine alpha, cosine beta, and we're going to let alpha be this angle in the first term, and we're going to let beta be just omega t, the angle in the second term. So making substitution for alpha and beta and then applying the trig identity, we come up with the following expression. And now what we're going to do is we're going to do one more simplification, and that is on this last term, because we still have this sum inside the parentheses. So now what we're going to do is say cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. We're going to let alpha be 2 omega t, and we're going to let beta be theta v minus theta I. So if we use that trig identity, then we end up with the following expression, which, as I said, initially looks more complicated, but actually is really convenient because each of these terms has some physical meaning that we can pull out. So notice first of all that the time term, the omega t term, first of all the frequency doubles. So in power, originally our voltage and current had a frequency of omega radians per second. You'll notice the power that has doubled the frequency. So the temporal oscillation of AC power is twice that in frequency of the current or voltage individually. Also notice that we have one term here that has effectively no time variation. So what that means is that we've got this sort of constant term that looks kind of like an average, and then we've got these two terms that vary as functions of time. So this first term we're actually going to define as the average power because it has no time variation. These other two terms, okay, anytime we have the cosine of an angle and we find its average, it's going to average out to 0. So this term and this term, sine and cosine of omega t, or 2 omega t, if we were to calculate an average value, that average value would be 0. So what that means is that averaged over time, this is the power that's present. But instantaneous power, by definition of the term instantaneous, has to include this time variation. So this is our definition of instantaneous power. So on the last exam in this class, I always ask people to calculate an instantaneous power. That's really not hard given a current and a voltage. That's not hard at all as long as you understand exactly what I'm asking for. All right, so if you were to plot this, it would look like this. Here's the current plotted, here's the voltage plotted. You see there's a phase shift in between them. And so you see then the instantaneous power looks like this. It has twice the frequency, so half the period. And you notice it's offset from the 0 axis. So the amount it's offset by is the average power. And you notice then it oscillates from a maximum to a minimum. All right, so we can rewrite this using a couple of shortcut terms, P and Q, where P is the average power and Q we're going to call the reactive power. And so this is another expression that you can use for instantaneous power, and it's possible to solve for P and Q first and then plug those into this expression for instantaneous power. So P is going to be our average power. Q is going to be our reactive power. Some textbooks will refer to average power as real power. In this textbook and in most of the textbooks that I have used, it's referred to as average power. So referring the P and the Q back to our original equation and comparing it to the one on the previous slide, we can say that P is the magnitude of the voltage times the magnitude of the current over 2 times the cosine of theta V minus theta I. This cosine of theta V minus theta I, we'll see a definition for it a bit later, but it's referred to as the power factor. The real power is the power that actually gets dissipated in a load. The reactive power is power that is trapped in the system due to stored energy in inductors and or capacitors. Hence it's called reactive. So for the average power, notice that if the current and the voltage are in phase, in other words, if theta V and theta I are equal, then you'll have the average power being Vm over 2, and the reactive power will be 0. If the voltage and the current are completely out of phase, in other words, they're out of phase by 90 degrees, then you have the cosine of 90, and if you have the cosine of 90 or minus 90, the average power goes to 0 and the reactive power is a maximum. You may recall that since the impedance of an inductor is j omega L, then if we use the formula V is Z times I for an inductor only, what the inductor does is it shifts the phase of the voltage by 90 degrees. A capacitor will from the current. A capacitor will shift the phase from current to voltage by minus 90 degrees. So what that means is that capacitors and inductors have no average power. They have only reactive power. The units for average or real power are watts, just like for instantaneous power. It also has units of watts. The units for reactive power are voltamps reactive, VAR, also referred to as VARs. Okay, so once again, if a circuit is purely resistive, then the voltage and current are in phase. That means theta V is equal to theta I. How do we know that? Because we know that V is equal to I times Z. And if the load is purely resistive, then we know that Z is a real number. And a real number multiplied by a phasor will not affect the phase. So for a resistive-only load, voltage and current are always in phase. I know that sometimes I say a lot of things, and it's hard to know what is really important long term and what is not important long term. So I'll just pause here and say this concept that if a load is real or if a circuit is purely resistive, the voltage and current are in phase is a very important concept, not just in this class, but throughout electrical engineering. And in fact, it is one of the key issues with power distribution, particularly when you're trying to take things like wind farms, put them on the grid, and deliver the power over a large geographical area, because you tend to get big phase shifts. Getting big phase shifts between current and voltage means that there's certain amount of power that you can't extract from the system because it's reactive. So this is one of those important statements. When the circuit between two terminals is purely resistive, voltage and current are in phase, theta V is equal to theta I. You have no reactive power, you have the instantaneous real power, and P, being the average power, is maximized. All right, and so here is just an illustration of the instantaneous power for a purely resistive circuit. For a purely inductive circuit, remember Z is equal to J omega L for an inductor. So the voltage is going to be shifted by, remember, J is equal to positive 90. You can visualize that on your complex plane. J converts into 90-degree phase. It has no real part, and so the average power, because theta V minus theta I is equal to 90, goes away. Your expression for the instantaneous power is purely reactive. In this case, it's purely inductive. Your negative sign from the original equation is retained. The phase difference between the voltage and the current is plus 90 degrees. We say the voltage leads the current in an inductor by a 90-degree phase angle. Okay, so we measure the power of purely inductive circuits using the reactive power Q. It just says an inductor is a reactance. It's a reactive element. Once again, average power has units of watts, and reactive power has units of VARs, or voltamps reactive. Okay, the graph of the instantaneous power, the average power, and the reactive power for a purely inductive circuit. The average power obviously is going to be 0. Q is going to be a maximum. The instantaneous power, once again, will have twice the frequency of the voltage and current. For purely capacitive circuits, we have essentially the same thing, except in this case, theta V minus theta I is equal to minus 90, and so when we calculate Q, we get minus 1 var. The average power, once again, is 0, and you end up with a purely reactive term. Now, the difference is when you plug in theta V and theta I and calculate Q, you get a negative 1 here. When you do that, because of the negative 90 and because of the equation for Q, if you do that for the inductor, you get a positive 90. So we can say that the reactive power is negative for capacitively dominated circuits, while it's positive for inductively dominated circuits. So here's a similar, I don't know how much use these graphs really are. Here's a similar graph of the instantaneous power The average power and the reactive power for a purely capacitive circuit. So the instantaneous is a sinusoid. The average power is 0. The reactive power is down here at -1. So let's talk a little bit about the power factor. So the power factor is important because it gives you a relative indication of how much of your power is average or real and how much of it is reactive. So for a given load or a given element or a given terminal pair, the power factor is the cosine of theta v minus theta I. Now, if whatever you're calculating the power for is purely resistive, theta v and theta I are equal, and the power factor is 1. So if you have a power factor of 1, that means your load, let's talk about load, for example. Say we're calculating the power factor in load. It means your load is purely resistive, and it means all of the power being delivered to that load is being dissipated in that load in the form of heat, because it would be resistive. Your reactive factor is sine of theta v minus theta I. This is not widely used. Okay, so we typically talk about the power factor. The power factor angle is theta v minus theta I. So the power factor is the cosine of the power factor angle. Now, in designing systems, in power systems, where the goal is to deliver power to a load, you would like to minimize your phase difference between the voltage and the current. The reason is that this cosine of theta v minus theta I is what shows up in your average power. And so if your theta v minus theta I is close to 0, the cosine is close to 1, meaning most of your power does get dissipated in your load. So when you look at things like transformers and motors and other devices that you buy commercially, you'll see ratings or specifications on those. And many times the specification will indicate the power factor. So what that means is whatever that is that you're purchasing, let's say you're purchasing a transformer, what that means is that you're not going to transmit 100% of the power to your load if your power factor for that device is less than 1. So some of the power is going to be trapped in the motor, trapped in the transformer, trapped in the generator, trapped in whatever it is you're buying. You're not going to get, if you buy a 10 kilowatt transformer with a power factor of 0.95, you're not going to get 10 kilowatts out to your load because your power factor is less than 1. So when you look at things like later on, you'll take lab and you may end up having to build things that have components that have a power factor rating. That's what that means. So the power factor is what you will see. No one ever talks about this, but it is about reactive factor, but it is a definition. Okay, so even if you know the power factor, you can't determine the power factor angle without additional knowledge. And the reason is theta v minus theta I, the cosine, basically the cosine of an angle is equal to the cosine of the negative angle. So in order to completely know what the angle means, we have to use the phrase leading power factor or lagging power factor. Okay, power factor is always done with respect to whether the current leads or lags. Okay, so lagging power factor would mean that the current lags the voltage and you have an inductive load. Leading power factor means that the current leads the voltage and you have a capacitive load. Okay, so it's important if you're going to understand what your load is, you can't just take the power factor. You also need to know is it a leading or lagging power factor, and you need to remember that leading and lagging are adjectives that define the current. So the current lags, the current leads. That's how the definitions are made. Why? Because when we originally set this up, we set it up with the reference of the current phase angle being 0, and we're using a standard complex plane notation to understand leading and lagging angles. So that's why that's defined the way it is. So I'm going to stop the video here because I understand it gets a little tiresome to watch lengthy videos, and we'll pick back up with an example.